Okay team, so we're motoring on and today we're looking at 10.5 connected particles. Before we do, have a moment to look at this multiple choice question based on what we did yesterday. Pause the video, try and find the right answer. Okay, so hopefully as you looked at these you realised that the key thing is that friction must always oppose the direction of motion. And that's possible with all of these. In this case, if P is bigger than the mg, or the component of mg acting down the slope, then the particle's going to move up and friction would oppose it. In this example, P is acting down the slope with mg, so friction would definitely be opposing that motion and acting up the slope. In case C, what we're looking at here is a very heavy object with quite a small force P. So the direction of motion is still down the slope, and the friction can oppose it, so this makes sense. In option D, there is no external force, but the mass of the object is causing the weight component to pull it down the slope, and friction opposes motion. Example E then must be the impossible one, because the only force acting parallel to the slope that could generate motion is mg, that's acting down, but friction could not be acting in that same direction because it has to oppose the motion. So the correct answer, the one which cannot work, is E. Good stuff. Alright, we're going to move on to connected particles today, and I love using this video when teaching this topic. You're going to see a really strong man, world's strongest man at some point in time, called Brian Shaw. And what I want you to do as you're watching this video is to create a sketch of the force diagram for this scenario. I want you to listen quite carefully to the commentary. I want you to try and make your diagram as sophisticated as possible based on what you see. Let's have a look. Okay, there we go. So Brian's tired. Let's have a look. I only got halfway through mine. But one way we could do this right is with a really simple diagram where we have two objects. We've got Brian, we've got the truck. They're connected by some kind of rope, which is going to exert a tension on both objects. It's going to pull Brian backwards. Let me label Brian. And it's going to pull the truck forwards. And so you can see the direction of those arrows there. And the tension is going to be the same for both, equal and opposite. I've got a small mass for Brian. I've got a big M for the truck. And let me throw in some kind of friction here as well. There's going to be some kind of coefficient of friction, and it looked like double arrow. It was accelerating forwards, so Brian was being successful. So here's kind of a starting point. But if we were doing this over several lessons, what I'd do is just build up with this example, because if you're listening to the commentary, at the beginning he said it was going up a slight slope. So we could try the same thing, but try it at a slight slope of angle theta. So Brian again pulling the truck. And then the other thing, which you might have seen is that because of the way that Brian was leaning, the rope was kind of acting upwards like this, and so we could say that that was also at a different angle of phi, and you could try and model that using the same kind of forces, but on a slope and with an angled wire. Now, we're not going to do anything quite so tricky. It's not quite within the scope of what we're doing, but I want you guys to see that it's possible just to add step by step some complexities into what we do just to improve the accuracy of the model. So if I were to work this out, and it's the same maths just with slightly more complicated steps, I'd add the fact that the weights were actually acting slightly against Brian, and so they're going to have a component that is pulling down the slope and resisting his tractive force, his pulling force. And then I would also allow for the fact that the tension that on Brian is having the effect of kind of lifting him up, and that's actually a negative. That would also reduce the reaction. Increase the reaction force on the truck, and so increase friction. But like I say, that idea of truck pulling, we can have in mind when we look at the kind of diagrams which we are going to consider. And here we go. Here's an example of one thing pulling another thing up a hill. The title of the topic is Connected Particles, and what we're looking at here is when we have two things connected by a rope or a string. And as mentioned at the beginning of the unit, when we do this, we're going to consider the strings or the ropes to be light, meaning they don't have any of their own mass, and in general we'll consider them to be inextensible, meaning they're fixed length, they don't stretch. And occasionally, like in one of the questions today, we might consider that they have a capacity that they can withstand, and we'll look at whether they snap or they don't snap. So, as you look at these diagrams, I want you just to stress a couple of things right from the start here. So in these first ones, we've got just two particles connected by a single rope, and we can see that the tension is equal and opposite in both of those. So we have like one rope, and then we have the tensions being equal. So T equals T, T2 equals T2. Here we've kind of got this extra pulling force, which is called T1 on this diagram. When we have a pulley involved, the effect of a smooth pulley is that it doesn't apply any friction to the rope, and therefore T still equals T. The tension is equal and opposite on both objects, even though the rope has turned a corner and the direction of motion has changed. So a key thing, if we see smooth pulling, then the tensions are equal. This example here, and this one here. However, this is the key point. If there are two strings or ropes, then actually it's very unlikely that those tensions are going to be equal. And in this example here, we can see, if we look at this setup, that there are two different ropes. We have, if we call this mass in the middle, like the main mass, we've got one rope that goes to the left around this pulley, and we have a completely separate rope that goes the other way. And therefore those tensions are not equal. We have to call them T1 and T2, and we have to consider them separately. If they are equal, it's purely by chance. So, bear that in mind when you're doing all the questions from the exercise. Let's have a go at one. We've got 3 questions to do today. Same principle as before. Don't do your working out in pen in the notes here. but have a go at the question, either in pencil or somewhere else. See if you can figure out how to work out the tension in the rope and to make a judgment on whether it snaps. Take a few minutes, pause the video, have a go. Alright, I'll go through this one now. Key thing always, start with a diagram. So let's have a look. I've got two cars. I'm going to call them, it doesn't really matter which way we go, but car 1, car 2. They're connected via a rope, equal and opposite tensions in both. What have I got? Reaction forces on both. Make it simple, R1, R2. And then 1 ton is 1,000 kilos. So the first car, the one that is pulling, is 1,000 newtons. So that would be 1,000 G. And the other one's 0.75 tons. Sorry, did I say newtons? I meant kilograms. 1,000 kilograms, so 1,000 G. And 0.75 tons here is 750 kilograms, so that's 750 G. And then we've got attractive force of 3,000 newtons, and we're expecting to see acceleration in the direction of that force. The other thing to notice is resistance to motion can be neglected. This tells us that there is no friction. So resistance to motion can be neglected, no friction. Okay, now with a connected particle question like this, there really are 3 things that we can do. We can either look at the first object, we can look at the second object, or we could look at the whole system. And typically you don't need to do all of those things to solve the question. And for this first one, I'm going to work through it by just looking at the car 1 and car 2. We'll get the answer, and then I'll talk to you about how you can use the whole system approach. So, first thing I'm going to do, and I want you to use this kind of language when you answer your questions. Consider car 1. That means I'm just looking at this car 1 part of it. Wish I'd got my diagram slightly bigger, but essentially the only forces I'm considering are the forces that are acting on car 1. Hopefully you can see that. Car 1. So, I'm going to resolve in the direction of motion to the right. I'm going to use Newton's second law, and I'm going to observe that I've got 3,000 newtons as an attractive pulling force, and then I've got tension acting in the opposite direction. Those are the only 2 forces with a horizontal component. The mass is 1,000 and the acceleration must be A. I'm just going to label that equation 1. Now what I'm going to do, some of you may see where this method is going to take us, is I'm going to consider car 2. So, blue pen. Now I'm only looking at the forces that are acting on car 2, blue box only. And in the horizontal direction, if I resolve in the direction of motion, the only force is T, and that is acting in the direction of motion. Mass is 750, and the acceleration is still A. And this is really the key to these questions, right? The acceleration is the same for both cars. And that's the key thing, because now what we see, I've labelled them 1 and 2, is I have simultaneous equations. From 2, A equals T over 750. And I'm going to sub that into 1. Acceleration equals T over 750, which means that 3,000 minus T equals 1,000 over 750 T, which is 4 over 3. So 3,000 equals 4 over 3 plus 3 over 3, 7 over 3t. Therefore, t equals 9,000 over 7. It says in the question here the rope is able to withstand a tension of 1,000 newtons. Does it snap? Well, this is clearly greater than 1,000. Therefore, the rope snaps. So, little track back. Key here was to split the system into two parts. In the first part, we looked at the forces acting on car 1 in the green box. Second, we looked at the forces acting on car 2, blue box, and we connected those because we knew that the tension and the acceleration is the same for both. Now, there is a slightly different approach to this, which is to look at the whole system. So what I'm going to do here is just go or whole system. And whenever we've got two things connected by the same acceleration and the same tension, what we can do is we can kind of draw a simplified overall diagram. I'm going to do that here. Now this is the whole system acting together. So this block represents both the car 1 and car 2. The driving force is still the same, that's pulling it forward. The mass is going to be 1,750 g. The upward force, a new reaction, just call it R, that's going to oppose that. And then there is no other force that pulls the whole of the system back. The tensions are kind of absorbed within this. And the acceleration of the whole system is clearly going to be the same as the acceleration for car 1 and car 2. So, if I consider the whole system, then what I can do here is I can say resolve direction of motion, Newton's second law, 3,000, that's the force, it's the only force acting parallel to motion, equals total mass is 1,750 A, therefore A equals 3,000 over 1,750. And if you take that and you sub it back into one of the other equations and you figure it out, that's the same acceleration we had before. So this represents, rather than that kind of part A, part B solution, this can represent a nice shortcut. Got a second example here. We've got a pulley. We've got three masses. We've got 1, we've got 2, we've got 3. And the whole thing's going to accelerate. And if we think about it for a second, we figure out that because the mass is bigger on this side compared to a total of 9 kilograms on the left, it's going to accelerate towards the right. So, I want you to try this question, but I'm going to give you a little bit of a hint, and I want you to use the whole system approach. So, I want you to start off by saying, consider the whole system. Now, it's a bit tricky because the rope bends around the pulley, but what we're going to do is we're just going to make it abstract. And we're going to take a combined block to represent the whole thing, and we're going to take the direction to the right to be the kind of overall direction of motion. And pulling the whole system to the right, we have a force of 11g. Pulling the whole system to the left, that's the opposite direction along the rope, we have 9g. And the combined mass of the whole thing would be 20 kilograms. So I want you to see if you can use this approach as a really good shortcut to get you into this question and avoid those simultaneous equations. Take a look. Okay, so hopefully you paused the video and had a go and had a real think about this diagram. And just one more time, what we're doing here is we're looking at the overall system and we're just thinking about the movement left and right. Is the rope going to move down on the right hand side here, or is it going to move down on the left? If I think about that, so I can't really say left and right anymore. So what I'm going to say is I'm going to resolve in the direction of motion, because its direction of motion is up on this side and down on this side. I'm going to use Newton's second law, and resolving, I've got 11g minus 9g equals 20a, which would tell me that 2g equals 20a, so a is g over 10. Now that is the fastest way that you could possibly find the acceleration here, because the alternative in the textbook and what they show you is that you set up 3 simultaneous equations basically, and we don't need to do this if we're comfortable with this whole system approach, which means you absorb the tensions. But for part B and C, as you've probably seen, now we do need to look at parts of the system. So it's asking for the tension in the string joining 4 kilograms and 11 kilograms, so that's going to be T1. And so what I'm going to do is I'm going to consider the 11 kg mass. What's going on here? Well, it's fairly straightforward. We've got 11g pulling it down, we've got T1 pulling it up, and we know the whole thing is going to accelerate downwards with an acceleration of g over 10 meters per second squared, and the mass is 11 kg. So, resolving in the direction of motion, which is down, Newton's second law, 11g minus T1 equals the mass times the acceleration, so 11 times g over 10. Rearranging, adding T1 to this side, subtracting 11g over 10 would give me like 99 g over 10 as my final answer. So T1 is 99 g over 10. And then for part C, they're asking for the other tension. It's probably easiest for me to take the bottom block. I could do it with either, but the bottom block has fewer forces acting on it. So I'm going to consider the 5 kilogram mass. And just notice, by the way, sorry, here we go. Just notice how helpful it is to write this stuff. Consider 11 kilogram mass, consider 5 kilogram mass, and to put your diagram with it. Like, genuinely really helpful to the person looking at your work. They can see what you're thinking. So, what am I doing here? Well, this time, it's a similar diagram to the last one, but this time I've got to remember to reverse the acceleration, because on this side, for this block, it's going to move up. The direction of motion is definitely upwards. So, resolving vertically in the direction of motion, Newton's second law, T2 minus 5g equals the mass times the acceleration. Rearranging, T2 is going to be 5g over 10 plus 50g over 10, so 55g over 10. Answer. So, a nice problem, right? The diagram looks complicated, but by making really smart choices about what parts of it we're considering, first the whole thing all together, then the 11 kilogram, then the 5 kilogram, we can isolate the thing that we're looking for and find it really quickly. Okay, hope you're still with me. One last question and an exam one. Probably easier than anything we've looked at so far, but does involve an extra dimension, and we've got things running at an angle. But take a moment and have a go at both parts A and B. Alright, so you paused the video and had a go. First thing I'm going to do for a show that question, right, and we're starting to get used to the fact that we really need to work hard on these. What I am definitely going to do is I'm definitely going to label this diagram really, really thoroughly. So, three forces acting on this block. It says the first rope with an angle of 30 has tension T1, so this one's T1. Second rope T2, angle of 60, and a mass of M creates a weight of mg. Then if I just put a vertical line up here, this angle is going to be 30 degrees, this angle is going to be 60 degrees, and that's going to enable me to find my vertical and horizontal components. If I think vertically, this one is going to be T1 cos 30, this one is going to be T2 cos 60, vertical component here. Maybe just to really show off for the people marking my work, I'm going to do my little triangle. It's a 1, 2, root 3 job. This is 60, this is 30, and because I know I'm going to need them, I'm just going to write sine 30 equals a half, sine 60 equals root 3 over 2, cos 30 equals root 3 over 2, cos 60 equals a half. And I'm just taking the effort to show that I'm deriving those results myself. And then, first mark's kind of easy. Resolving horizontally, because I'm not interested in this m, that's an extra variable I don't know about. If this is in equilibrium, then the horizontal components must balance. So if I resolve horizontally with Newton's second law, I've got T2, horizontal component is the opposite, so that would be sine, T2 sine 60, minus T1 sine 30, has to equal 0, because the acceleration is 0, it's in equilibrium. So, what we got here, T2 times root 3 over 2 minus T1 times a half equals 0, and we simplify that, T2 equals 1 over root 3 T1 as they require. Nice. Okay. What's going on now? The first rope is strong, but the second rope will break if the tension exceeds 98. Second rope, that means we're talking about T2 here. Find the maximum value of M for which the flower pot will remain in equilibrium, and going for 3 marks. So I've resolved horizontally in the first part. I'm definitely going to be resolving vertically now, but what I'm going to do is I'm going to assume that it's in equilibrium. That's what this whole question is about. They're saying if it's in equilibrium, what's the maximum the mass can be? And I'm going to resolve vertically up Newton's second law, and what I can see is I've got T1 cos 30 plus T2 cos 60 minus mg equals 0. And then what I'm going to do is I'm going to substitute in using my part A, and I'm going to eliminate one of these. Now, you can do it either way, but because we're interested in T2, I'm going to sub out and I'm going to put T1 equals root 3 T2. So root 3 T2 times cos 30, which is a half, plus T2 times root 3 over 2 equals mg. Adding the mg to the other side. So what have I got here? Root 3 over 2 plus root 3 over 2 would be root 3. So root 3 T2 equals mg. And then it's saying that the maximum value of the mass, so that the tension can't be over 98. So max value of T2 is 98 newtons. Therefore, the maximum mass would be root 3 times T2 over G. So that's root 3 times 98 over G. And I've not put that into my calculator, but whatever that answer is, that's your maximum mass. Alright, motoring on with this stuff now, and Lots of different force type problems to consider. I'll need to give it a good go over the weekend. You've got a few days to get your heads around it all, and then we will crack on with the second half of this final topic next week. See you all soon.